These are the numbers that we have all been familiar with since preschool, and we use these numbers every day. 1 apple, 4 bananas. But what if we had a bit less than an apple? What number should we use for someone who ate more than 2 bananas, but surely less than 3? In this case, we're looking for some new numerical entities in between our everyday natural numbers. Luckily, we don't have to work too hard to pick some of them, as these colorful segments are seething with numbers also known as decimals. Now, each of these colorful dots between whole numbers represents a decimal. So even though we don't know exactly the decimal that this dot represents, we know for sure that this mystery number is greater than 0, but smaller than 1. Similarly, we deduce the inequalities for other decimals on the number line. Now let's put all these dots back where they belong. The truth is that while whole numbers can be found only at specific points on our number line, decimals can be found practically anywhere in between. And although our number line seems to be packed with decimals represented as colorful dots, if we take a closer look, we will notice that there is still some room for more dots, meaning more decimals can be found between any two decimals regardless of how close they are. The more we zoom in, more and more decimals will come into visibility. Now the question is, how decimals look like as numbers? What kind of digits should we use and in what order? If we used numerals, this dot would be exactly 4.3, but why? Well, the first digit, number 4, is the whole part that we are familiar with. But the second digit, number 3, shows how far from number 4 our decimal is. To understand that fractional part of our number, as we call it, we need to see in more detail how small it really is. So let's take a closer look in the neighborhood of 0. Here we have 3 identical number lines divided into line segments of equal length. The third number line also contains segments, but they are too close to each other to be visible. But if we zoom in, we can clearly notice the small gaps in between. As we scan the number line, the number that appears after the decimal point is exactly the number of the segments covered at that time in each line. The only difference is that in the first line we keep counting more numbers, but in the end, all the creatures stand right in the middle of the exact same line, that is, they have arrived at the same number. That's why 0.5, 0.50 or 0.500 is the exact same number. Now let's have a look at these 3 numbers. The number at the bottom of the screen is the smallest of all 3, as its distance from 0 is the shortest. So the fact that a decimal has more digits on the right of the decimal point doesn't mean that it's necessarily greater than a decimal with fewer digits in its fractional part. Just like natural numbers tell us how many whole objects, let's say, we have in total, decimals can show how much of an object or a quantity we have. In this example, we explore how the total amount of a quantity changes as we multiply it with numbers smaller than 1. So here we have an apple, or what's left of it approximately according to the decimal number we use to express that quantity in this rather unusual equality. From nothing, that is 0, or almost nothing when we are close to 0, to a whole apple and anything in between. The closer we get to number 1, the closer we get to enjoy a whole apple. It seems that whole numbers don't tell us the whole story. We need more and more numbers, the numbers in between, to fill the gaps in our narrative and understanding, so that we can better and more accurately describe the world around us and everything in it, like objects from our daily lives. Just like this car we've got right here, and some details about our little trip with it that we can actually measure. From the time elapsed, distance traveled, average speed, everyday heights and widths, to cosmic distances and of course universal numbers, also known as physical constants that appear in nature, uniquely characterizing the universe we live in. And on the other hand, we have some other quite special numbers too, whose origin is purely mathematical and can indeed help us study the world around us. Pi is a good example. It's approximately 3.14, but in reality this number, apart from being long, really long, and which is basically the circumference of a circle with diameter 1. As we can see in this rather short animation with the aid of a rolling circle, appears also in the most fundamental mathematical expressions and models we have available to study a wide range of phenomena and ultimately make sense of the cosmos. All these mathematical expressions, numbers, mathematical or physical in origin, with the insane amount of accuracy they provide in our view of the world, are part of a bigger picture showing not only the unreasonable effectiveness of mathematics in natural sciences, but also suggesting that the universe we happen to live in may be in fact entirely mathematical.